Thank you. I'm delighted to be here. It's been a great day with great talks. This is my second time in China in 2 months to talk about big data. It's a phenomenon all over the world, and there's lots to do. If you're a student looking for things to work on, this problem is just getting started. So one of the main things I want to do today is introduce some of the conceptual issues surrounding big data. It's the kind of field where one person sitting in a room thinking about the problem can actually have a really big impact, which seems kind of surprising because you think you would need huge numbers of computers and huge amounts of data to work on the problem, almost by definition. And I hope by the end of the talk you'll be convinced that that's actually not the case. So there's a phenomenon which I don't really have to spend much time on. I think everyone knows about it. There's huge amounts of data being collected, and John Hopcroft's talk sort of reminded you of some of this. One of them factors is big science generates huge data sets. Astronomy, particle physics are good examples, genomics. The other is information technology, which is the one which is perhaps more present in all of our minds. Activity on the internet, generating massive data for personalization. And then linking these sensor networks are becoming pervasive. So that's the phenomenon. But what's the intellectual problem really? Is it just big? Is it just more storage, more capacity, more of everything that solves the problem? I'm going to argue no. Computer scientists think about the world in terms of resources. The classical resources have been time and space that have sort of underpinned the field for all these years, and energy to some degree. Data has not been thought about really as a resource. It's the things you apply resources to. Okay? But what's new is that data really now is being viewed as a resource, something you give me that I make use of and get value out of, and I get knowledge out of it. So if it's a resource, we have to combine it with all of our other resources like space and time and worry about the trade-offs in designing a system that takes into account that we have some data resource, we have some time, we have some space, and they trade off in various ways. The funny thing about data, though, is that it's an unusual resource. It should be the case with any resource, the more of it you give me, the happier I am. All right? If I give you more time, more space, you're happier and happier. And with data, that's not the case. And so if you go into a company and ask them what's their biggest problem, the problem is they have too much data. And so in our current state of knowledge, it's really, really the case that more data causes more trouble. And we have to work around this issue. So there's two reasons for this. One statistical and the other is computational. The statistical one is maybe a little more subtle, so let's spend a little time on that. So let's think of like a database person thinks. Our data is an array, a table. The rows are, say, people, and the columns are descriptors of people. So classical databases, maybe you had 1,000 rows, 1,000 people in your database. How many descriptors would you need? Well, maybe not a few, not more than a few. Say where the person lived, their age, their height, their income. And that's enough to kind of make some of the distinctions you might care to make in a database. Now we're thinking about billions of rows because we're really interested in all the personalized details of all of you. So if you live in Tianjin and you like to ride bicycles and you love Michael Jackson, what's the probability you're going to click on my ad? Or what's the probability that you're going to have a certain disease? Or et cetera, et cetera. We're interested in every single one of you. So we have data about all of you. Okay? So the number of rows are growing somehow linearly. Maybe the number of columns have got to grow too because we're interested in all these distinctions. Maybe some of the columns are your genome. They're what food you ate yesterday. They're your preference in music, what books you like to read, and so on and so forth. We'll collect all these things. The problem is that we're interested not just in the individual columns. We're interested in combinations of the columns. Okay? It's if you live in Tianjin and you like to ride bicycles and your favorite food is Kung Pao chicken, then will you do something. That's a particular combination of all the columns. And the problem is this. I have an exponential number of combinations of the columns. So if I have a linear growth in rows, linear growth in columns, I have an exponential growth in the number of things I'm considering. So let's think about a medical example. Let's suppose one of the columns is liver disease. All right, so I'm interested, and I look at all the ones. Every time I see liver disease, that's a 1. If it's a 0, you didn't have liver disease. So let's now look at all the cases where there's liver disease. There's going to be some combinations of the columns which is going to perfectly predict liver disease. All right, maybe it's you live in Tianjin and you like to ride bicycles and you eat bananas. All right, every such person had liver disease. All right, so now you arrive at the doctor and they say, well, where do you live? And you say, Tianjin. And you say, what do you like to do on Saturday? Ride bicycles. What's your favorite food? Bananas. They say, we have to take out your liver. I'm sorry. All right, and so the problem is that in any data set, if we have exponential number of things we're looking at and linear numbers of items in which to verify those things, we're going to find meaningless patterns just by noise alone. All right, and so as data get bigger and bigger and bigger, this problem is getting worse and worse and worse. Okay, so big data is not this wonderful thing, give me all the data, I got all the knowledge in the world. Big data is a big problem. Give me this data, it's harder and harder to turn it into knowledge, real meaningful things that are real that we can act on and believe. Okay, so now statisticians worry about these issues. This isn't new. How do I get rid of the noise and get rid of the bias and get the knowledge out? But statistical procedures are themselves algorithms, and they take time. And we have to run them on the computer. And maybe in big data sets, they take too long. All right? I can't make quick decisions anymore. So we really have a really big problem on our hands. We don't know how to run statistical procedures and make good decisions quickly at scale. All right? So in fact, the second reason, this is a long slide, but it's an important set of points. The first reason is statistical. The second really is computational. Algorithms take a certain amount of time to run, say n log n, n cubed, n squared. All right, suppose I need to make a decision in a second, like in an online auction, or less than a second. All right, you start giving me a certain amount of data, and my n log n algorithm is perfectly good. It'll run in 1 second. But now you give me more and more data, and suddenly n log n is not going to finish in that allotted amount of time. What do? I have to start maybe throwing away the data, but what rate do I throw away data? It could be my statistical error will grow if I start throwing away data too fast. I have to throw it away more slowly, but now it'll take me too long. All right, so we really have a big problem when we bring together time with statistical error with growth in data set sizes. We don't have algorithms that will gracefully scale to larger and larger data. All right, so these are real problems. If you go to industry and look at groups that have really large data sets, these are the problems they're facing, and I view these as fundamental and difficult. Here's one way to say a theoretical goal that tries to get at this. Given an inferential goal, that's a statistician's kind of goal, usually a risk function, and a fixed computational budget, a minute, a second, an hour, provide a guarantee that the quality of inference will increase monotonically as data accrue without bound. So the without bound is really like a computer scientist. I don't want to have to face this problem every generation. I want to face it once and for all. What are the principles that scale statistical risk against time? And I think we're very far away from being able to solve this problem. I think this is going to take several decades to solve. So I'm going to talk about a little bit of progress we've been making. We've been working on this. One of them is kind of a bottom-up problem. We're going to try to bring algorithmic principles more fully into contact with statistical inference. And I'm going to go to my favorite algorithm principle, which is divide and conquer, and tell you about how it relates to statistical inference. And it's an interesting, almost paradox. Statistical inference is about aggregating things, bringing things together. The more things you bring together, the smaller the error bars are, the better things are. Divide and conquer is about somehow separating things out, so they somehow fight each other. The basic ideas in statistics and computer science are somehow a little bit in conflict, and that intrigues me. So I'm going to talk about that. And then we're going to go back to this more theoretical problem and talk about how to trade, or what does it mean to trade off statistical efficiency and computational efficiency. All right, first problem, something we call the big data bootstrap. So I acknowledge some of my colleagues at Berkeley. I've been working on this for a couple of years now. The bootstrap is a solution to a really important problem, which is to assess the quality of inference. Most machine learning research doesn't worry about the quality of inference. You have an input, it goes into some box of some kind, and out comes an answer, say 9.5, right? But most statisticians aren't satisfied with that. They want to know what the error bar is on that 9.5. So for example, if the number was bigger than 10, you're going to take out your liver. Okay? And the number came out 9.5. Right? Well, is that really 9.5? Is there a big error bar? Is it possible that it's actually bigger than 10? Or is it really clearly not bigger than 10? All right, to make real decisions in the real world, you have to have error bars. All engineers know this, and we computer scientists should know this as well. So I've in fact worked with people in the database community trying to build databases that query comes in, out comes an answer with an error bar on every single query. That's what we should be doing as real-world engineering-oriented people. Error bars everywhere. Okay, so let's turn to a different field, statistics, and ask how do you get error bars on things? Well, this is kind of interesting. on very simple things like the sample mean, there's a formula. You can take an elementary stat class, and you'll learn that if you calculate the sample mean and it's 9.5, there's something called the standard error of the mean, which is a formula. It's something like the sample standard deviation divided by the square root of the number of data points. And so you plug that in, you get an error bar. All right, but what if you didn't calculate the sample mean? What if you calculated the median? You sort the data, you find the thing in the middle. That's called the median. And that came out to be 10.2. What's the error bar on that? Well, there is no formula. Right? So how do you get an error bar on something like the median? Right? Well, there is an answer. There's something called the Bootstrap, which will allow you to do that. It's a generic procedure for calculating error bars. And the problem is that Bootstrap doesn't scale to large data. So we're going to talk about that. So what's the quality of inference issue? So we have data x1 through xn. A machine learning or stat person might calculate some kind of a prediction or a parameter estimate based on the data. So I'm calling it a parameter, but it could be the output of a classifier. It could be any kind of prediction. Let's call it theta n. I'm not interested in this talk about theta n and procedures for scaling that black box. I'm interested in the quality of theta n. What's the error around it? Okay? And there are procedures for calculating that, not just the theta n, but the quality of theta n. Okay, so here's what you would do if you're an ideal frequentist statistician. This is almost the definition of being a frequentist, which is that you wouldn't just have one data set of size n, you'd have multiple data sets of size n. And on each data set, you calculate your median, say, or your other estimate. Okay? And now because they're different data sets, they're going to fluctuate. And you'll look at the spread of those things, and that's your error bar. Okay? That's almost by definition what you mean by an error bar. It's the error you get on multiple realizations of the data. All right? Well, you don't have multiple data sets. If you were the supreme being in heaven, you could do this again and again and again, generate data and look at the fluctuations. We only get one data set. All right, so let's think conceptually about how you might be able to, nonetheless, get around this issue and get error bars even though you have only one data set. Well, the data came from somewhere. There's an underlying population up there in heaven that generates data. And so let's make a little histogram-like object here, a distribution reflecting that underlying population. All right, so if you were the supreme being, if such a thing exists, you up in heaven, you'd be able to do what we have on this slide here. You would take the population, you would generate one data set, two data sets, m data sets. And on each one of your data sets, you'd calculate the thing you care about, the prediction, theta 1, theta 2, theta m. And then they go into some formula for the spread, and that's your error bar. All right? Now, one nice thing about this is that if the supreme being has a parallel computer, he or she could do this in parallel, because you can generate these data sets in parallel. Each computer goes off, computes the estimator, and then gets it all brought back together to calculate the error in the estimates. Okay, now, we don't have multiple data sets. We can't do that slide, but what we can do is the following. We observe that if there's an underlying population, the data came from that population, and we can think of the data not as a list of numbers now, but as a histogram. You probably all know how to make histograms, right, out of the data. The histogram itself is a distribution. It's called the empirical distribution, but it's a distribution. It can be used to generate more data, because it's a distribution, even though it's not as curvy as the one up there, it's itself a distribution. You can sample from it. All right, so there's this beautiful idea, which is called approximation, which is that empirical distribution approximates the truth, because it came from the truth. All right? And so you can pretend now that you don't have that underlying truth, but you have this approximation of the truth. And now you can live in a world where you're the supreme being, and that's the truth. And you can generate data from that truth. And you can do it not just once, you can do it multiple times. So it's a very subtle but very deep idea, which you can take one data set and from that generate multiple data sets. That idea is called the Bootstrap. And it's due to Brad Efron in 1979. He got a National Medal of Science in the United States for that. So talk about awards, that's kind of the biggest one you can get for this very simple idea. One person sitting in a room thinking a little bit about the problem and realize this can be done. So here's the picture. You take in the data, and from the data you form a histogram, and you can sample from that histogram multiple times, m times, say. You can do this in parallel. Even though this algorithm was developed in '79, there was no cloud, no distributed anything. This was a perfectly parallelizable procedure. Okay? And then you bring that all together on your central server, and you've got an error bar now. And so you could do this for any query. You could do why can't we have all of our databases doing resampling on the cloud? Sounds like a wonderful idea. And that's sort of the thing that I thought about a couple of years ago. Why don't we put the Bootstrap into computer scientists more fully? But there's a gotcha. So let's think about a terabyte of data sitting maybe on a server somewhere, or maybe it's already distributed. If you resample, if you take that data set and you do what I said, you take it and you sample from it. Well, I should go back here. Can I go back with it? Yes, I can do this. All right, what does it mean to sample from that histogram right there? I should make this clear. All right, well, it was based on n data points, but forget that. That's gone. It's now just a histogram. It's a distribution. I can sample from it any number of times I want. But let's sample from it n times, because that's the scale our data occurred on. And so I need to sample from it n times to get the same size data sets. All right, now I can do that once and do it again and again and again. What does it mean to sample from a histogram? It means to take one of the points. It's a discrete distribution. So I'm going to get one of those points. It's discrete. And I'm going to get it with proportion to the, probability proportion to the height. So I get one of those points, and then I do it again. I could get the same point over again, or I could get a new point. And I do this again, and I do this n times. Some of the points that formed that histogram I'll get several times, and some of them I won't get at all. That's exactly the same as sampling with replacement. I take out a thing, I put it back in. I could get it again. I could get it again, and maybe I could get a different one. All right, so the Bootstrap is often described as take the original data, resample it with replacement n times, and do that many times. That's the Bootstrap. Okay. Now, if I sample a terabyte, if I sample n data points with replacement, you can do a little mathematical calculation and see you get 0.632 of the data points occur in your resampled data. If I had a terabyte, that means I get 632 gigabytes. All right. Now, I'm not going to send 632 gigabytes off to my 200 servers so I can do the Bootstrap. That's going to hopelessly blow away my network. All right, so you can't do that with a terabyte of data. This sounds like a bad problem. This is our main procedure for getting error bars on arbitrary estimators. We can't do it at scale. And it's going to only get terabytes, small data these days. All right, so this is a serious problem. All right, so there is another, statisticians worked on this for a little while. They weren't thinking about computation very much. They were thinking about theory. The Bootstrap fails in some cases, actually, and another procedure came out that fixes some of those theoretical cases. It's called subsampling, but it seems like it's the answer, and it's not going to be. But let's think about this for a minute. So subsampling is the same picture as before. There's an underlying truth. You get a data set and form the histogram based on that. And now what you do is you say, well, n is too big. Let's now take a subsample of size b, maybe size squared of n, to really bring it down a lot. Now I can go compute my estimator on the b points, and I'll get a certain number, 9.5. But I could now do that again, because there's many ways of taking b points out of n. So I could do this many times, and I'm going to get some multiple values of the estimator. I'll get some fluctuations. All right, so it sounds pretty good. Out of one data set, I'm getting multiple values of the estimator. The problem is that if you just do that naively, that's wrong, because b points, the size of the error bars depends on the number of points. Right? If I have lots of points, I'm going to get small error bars. Small numbers of points, big error bars. The sample, you divide by square root of n for the classical sample error, standard error of the mean. All right, so I'm going to get fluctuations, but they're going to be on the wrong scale. And for statisticians, it's everything. If you get the wrong size of the error bars, you're just wrong. Okay? All right, so you can't subsample and just naively compute estimators and then return that as the answer. That just gives you the wrong answer. And this seems problematic because you have a really big data set. The only thing I can think of doing is taking smaller subsamples of it. It just seems you have to do that. But you get the wrong answer. So these guys who propose this realize this, of course. And this key issue arises that you're on the wrong scale. So they said, well, let's take that estimate, that error bar, which is now too big because I had smaller data sets, and rescale it so it's now on the right scale. Right? But how do you rescale? You need to analytically correct the error bars, and you don't know in general how to do that. So for some black box that somebody in a database system put in, a so-called user-defined function, you don't know how the scaling is. For a classical estimator like the mean, it's the square root of the neighbor data points, but that's not true for other estimators. Okay, so anyway, that's a problem. You'd have to do theory for every single black box that someone put into your database. That seems a little bit problematic. But there's even a worse problem, which is that if you try this in practice, it's an engineering defect. So we did a bunch of experiments. Here's one example. We took 50,000 data points of synthetic data. It's a 100-dimensional space. That's what D means. And we do least squares and calculate the error bars. And then because we did this synthetically, we know the true error bars. And we can compare and see how good our error bars are. All right, and so here are the results of doing that. Actually, maybe one more point on this slide. If you'll see up there, do I get a button? B of n, the next to last bullet, B of n equaled n to the gamma. So that's a fraction. So n to the 1/2 is the smallest size we take, and n to the 1 would be no subsampling at all. So we range between 1/2 and 1 as our subsampling procedure. All right, so on this slide, you see the error, which we can compute because we have its synthetic data. And you see on the x-axis time as this algorithm is subsampling away and running and running and running. And the different curves are the different values of that gamma exponent. All right, so you see when gamma is 0.5, which means square root, that's the black curve at the top, the error is terrible. Actually, I should say first, the blue curve is the bootstrap. So that's kind of our gold standard here. We know the bootstrap gives correct error bars. There's a theory behind the bootstrap. So you can see as a computational object, it sort of comes down pretty quickly and stabilizes to some fixed error. Because the number of data points is being held fixed here, the error doesn't go to 0. It sort of stabilizes at some value. Anyway, with square root subsampling, it just fails. It's that black curve at the top. It's not approaching the bootstrap in reasonable time. When you get 0.6, that's the green curve, it's still failing. Now, 0.7, 0.8, those are the curves below the blue curve. There, it's beating the bootstrap. It's a more efficient use of the computer than the bootstrap, which is kind of surprising. The bootstrap is viewed as really, really efficient. It has 1/n convergence instead of 1/square root of n, like the central limit theorem. It beats the central limit theorem, which everybody was pretty surprised about when that was proved in the 70s, 80s. So for those values, it actually beats the bootstrap. That's pretty cool. But now, for 0.9, it goes, that's the light blue curve, it fails again. So there's a little, it fails, it succeeds, it fails. There's a little range of gamma where it succeeds. But that value is not known a priori. It's problem dependent. We knew the truth here, so we know the right value, but you wouldn't know that in practice. So as an engineering solution, this isn't workable. Okay, so we have another idea. This is called the bag of little bootstraps, which does solve this problem. All right, so it's going to work with small subsets of the data, so it's a divide and conquer procedure. All right, so it's appropriate for distributed computing. All right, but you don't have to do any analytical rescaling. It somehow magically can get the right scale even though it doesn't rescale analytically. All right, so it's a little simple idea. Even though Bootstrap's been around for 40 years, statisticians weren't thinking about the computational problem of scale. So they didn't really worry about this issue. So here it is. Here's the idea on a couple of slides. Let's go back to that picture where we had the underlying truth, we had the data we get of size n, and we took a subsample of size b. So we're going to still think in those terms. Okay? Right, but now notice that the data of size b also come from the truth. They went through an intermediate step, but forget that for now. They also are coming indirectly from the underlying truth. All right? So you form a histogram based on your subsample. It also is an approximation of the truth. It doesn't look very good in my little picture here because n is now 10, but think about terabytes and gigabytes. It'll be also a good approximation of the truth. Okay, so now forget that you ever had the truth, and now you're in a world where you're the supreme being, and that is your truth. And you can sample from that. It was based on b points, but it's a distribution. You can sample from it as many times as you want. And so here's the key conceptual step that any of you in the room could have thought of, which is that you take that object, even though it was based on b points, and you sample it n times. You now are on the right scale because you got a data set of size n, which is what you needed. Many of the points there are going to repeat it many, many times because it's only b points, and that's small. And you're sampling it many, many times n. Okay? And some of the points might not occur at all. Okay? Now, you had b points, which is really small. Now let's think distributed. Okay? I got my little subsample of size b. I can send that to one of my processors on my distributed servers. Okay? I don't want to explode that back up to size n, either on the network or locally. That would be stupid. But I don't have to. I just keep a count of each of the B points, how many times did it get subsampled. Okay, so it's computationally efficient wherever you put the data. All right, so we can take that object right there and sample that n times, and now we're back on the right scale. And we can do that multiple times and do the bootstrap, starting with that object instead of starting with the original size histogram. All right, so we bootstrap the subsample. We're putting together subsampling with Bootstrap. All right, so I'm going to show you a picture here which summarizes. It's a now two-loop, it's a nested procedure. You take your original data on the left there, you take a subsample of size B on one processor, and then you bootstrap that subsample, resampling it with replacement n times, not B times. You get out now a bunch of estimator values, and you plug that into your formula for your error bar. So that top box there is on one processor. It got a bootstrap error bar, which is actually a correct error bar because it was based on samples of size n. Okay? All right, so why don't we just have one box up there? We've solved the problem with one box. Well, it was based on one subsample of size B, which is small, right? And so it's going to be correct but noisy. So whenever you have something that's correct and noisy, just average. So we're going to think about now the fixed one quantity. There's a third dimension here, which is the statistical risk, error. How much error do you have? All right, so you really should do a three-dimensional plot. But what we're going to do is think about fixed risk, like, accuracy of 0.01. I want to make sure you guarantee me I have accuracy of 0.01. And now you can trade off time and samples to achieve that in many different ways. All right, so look at some regions on this plot. A statistician would say, well, there is a certain, if you want to achieve a certain fixed risk, at some point you have to have a certain number of samples or you can't achieve that. Below that number of samples, it can't be done. That's called Minimax theory in statistics. So there's a well-known theory, and it has its independent of runtime. Whatever algorithm, you can't do better than something. That's Minimax. Similarly, in computer science, there's some notion of a lower bound, all right, that you can't solve a certain problem below a certain runtime, no matter how many samples we're talking about. Now, this is a little harder to kind of think about because it depends on the computational model, but it's sort of there, implicitly in computational complexity theory. All right, so we got to think about actual real algorithms as points on this plot. They achieve a certain risk with a certain runtime and a certain number of samples. And presumably, most good algorithms will be on a curve like this. A stupid algorithm would be up there to the right. Okay? So we're going to use all those algorithms as we weaken our algorithms as we get more and more data. All right, so we've thought this through, and I'm going to kind of go quickly now. I'm running out of time a little bit, but in a so-called denoising problem, kind of a very classical place where we can actually get some analytical results. So denoising means you give me data y, which is a noisy version of x star, where z is the noise with some scale, sigma, and I want to recover x star from y. Okay? How can you do that? Well, I want to imagine my possible solutions are on a set S. So that was at the very top. The signal comes from some set S. Maybe a sparse vector, as John Hopcroft talked about, and I want to recover that with some high accuracy. All right, and so a way to set this up as an estimation problem is you say, let's solve a convex problem where I take my sample mean y bar, I try to find that x which is close as possible to y bar, ranging over x in the set S. That's the natural estimator there, in the set S. Okay? Maybe S is now a complicated object. I can't do this. I could put a convex relaxation here and minimize over the set C, which is a convex relaxation of S. All right? So a picture makes that clear. Maybe S is a discrete set, of sparse vectors, and I can look at the convex whole of them as my first C, which is a convex set, and talk about characterizations of estimators with respect to C and not S. Okay? And in fact, there's a notion of a cone there, which you can see on the right, which is defined up there. It's sort of around the optimal point, all the directions that lead you to stay inside the feasible set. All right, so here's our here's a theorem we were able to prove, which is going to lead to some results, which is that the risk of any estimator based on that convex set C is upper bounded by, the left-hand quantity there is the risk, so I want to get an upper bound on that, an expectation of something called a Gaussian complexity. So I'm doing a little bit of math late in the day here. I apologize for that. But if you want to read more on Gaussian complexities, it is an object studied in functional analysis and in empirical process theory. It's called the Gaussian complexity. And it's going to be our guide to get to working on this trade-off curve. Okay, so we can compute the Gaussian complexity. All right, so corollary of that theorem is that if you want to achieve a certain risk, you have to have a certain number of sample points, which is bigger than that upper bound. Okay? All right, so that was with one C, but maybe that C is also computationally hard to work with. It requires n cubed or n squared to work with that C, to do optimization over that kind of set. So let's look at some weakenings of that set. So C prime might be a little bit bigger and a little bit easier to work with. And in general, we can get a hierarchy of these things, and these things have been studied in applied math and combinatorics and theoretical computer science. They're called relaxations. You have various forms of them shown there. And they are ordered by computational complexity. And what we're talking about is ordering them by statistical complexity and then trading them off. All right? So in the context of this denoising problem, you can carry this mathematical program out and get results. And so here are a couple of examples. If our set S consists of the set of cut matrices, and again, I think John talked a little bit about that, what that set means, then you can characterize the runtime and you can characterize the sample complexity, and you see results which are super polynomial p to the 1.75 for runtime as you look at complicated C's and simpler C's, and you can, so the runtime is decreasing, and the sample complexity is staying fixed at square root of p. So this tells you you can go to much simpler algorithms when you get big data and not lose in statistical risk at all if your problem is to optimize over the space of cut matrices. And we've done a bunch of other examples. Here's just another one for quickly. If your signal set is all perfect matches in a complete graph, then if you work with the convex hull of that, your runtime is lower bounded by p cubed. If you work with another relaxation called the hypersimplex, it goes down to p to the 1.5. And then we similarly can get results that go as square root of p for the sample complexity. And so now we actually really have trade-offs. We have statistics in the right column, computer science in the middle column, and we can move up and down these columns simultaneously to get a desired level of accuracy within a fixed runtime. Let me skip over the last example, but just to say that, that you can now go to many of these hierarchies and carry out the statistical analysis as well. Okay, so one of the big take-homes from this analysis so far is that it turns out that as compared to theoretical computer science, where the goal is not to get statistical risk, it's to get accuracy up to some approximation ratio, there, weakenings really can destroy your accuracy. Right here, because we're trying to worry about statistical risk as a quantity, we don't care about arbitrary approximation ratios. It turns out that the simple algorithms can give you very, very effective procedures that scale surprisingly well to larger and larger problems. So the fields of theoretical computer science and optimization theory and applied math have often studied these objects, but again, not thinking of them as statisticians, thinking about them from the point of view of kind of raw approximation ratio. Okay, I am now finished, and I've done that in time. One kind of meta point here, I alluded to earlier, is that I hope you see that there wasn't a lot of talk about building computer systems here. I think that's fantastic and important research in and of itself, and programming and software and all that. This was about the conceptual problems of big data. Thinking through what are really the problems I'm trying to solve. When can things go wrong? When can things be made correct? What are the algorithmic consequences of that? And this is really just getting started. Very, very few people have been thinking about this because computer science has been worried about one class of problems, statisticians another, and they've never been thinking about them jointly. So the other meta point then is that if you didn't understand a lot of this talk, it was a bit technical. It may be that you probably should go take some statistics classes if you're a computer scientist. If you're a statistician, I don't know if there are any of them here, you probably should take some computer science classes. All right, the future is for those people who can take these two fields and integrate them in one brain, not have to bring in every project a statistician and try to get them to talk to the computer scientist using some translation software. But one brain can bring those ideas jointly together. How do I think about my statistical risk, the errors I'm going to make when data come into a computer, and how do I think about scaling that so I don't have it break when I get more than 100,000 data points? All right? That's just not been what we've been teaching students. And so, we're still not doing a very good job of teaching students that. I think we may talk about that later. Right? So even though there aren't classes on this, you guys can go and learn about it yourself. If you're taking computer science classes, take a few stat classes or pick up some books and sit them by your bed and read them every night. And make sure you learn how to do these two things together. That's the future of this field. Thank you.